And this work was done here at BPF, and it was part of the thesis of Jules Larrea, so it's mainly his PhD work. And I will present the work. Okay, and this will be a very simple talk about what we are doing here at CPTF. I will take the opportunity to show you our lab and the techniques we have here. And there'll be not many pictures, but I will present mainly some pictures of the laboratory where we develop this kind of studies. Okay. I have to get used to this. No?
No, it has to be.
Okay.
It's just a pointer.
It's just a pointer? Ah, okay. Okay, these are the main collaborators in this work with cerium and platinum and Heavy Fermions Under Pressure. The first sample, the cerium platinum, was brought by Professor Andreas Aschler from Braunschweig. And the other sample was provided by Professor Elmegid, but it was prepared by Geibel in, I forgot the place of Geibel, Dresden. And then the theoretical support was given by Professor Musso Continentino, that is always collaborating with us. Okay. This is the formation of our group. We have several students, master and PhD. We have many postdocs, and we have the group is mainly made by Elisa and me and Isabel. And these are our collaborators at BPF and NUFI, and also Hortêncio from PUC and Pascal Pariudo from UNICA. But for this work, mainly Professor Musso is giving his collaboration. Okay. Now our main research area is strong correlated electron system under extreme conditions. We call like this, and we do high pressure, low temperature, and applied magnetic field. And we work mainly with high tensile ceramics and heavy fermions. Okay, and I myself work more with heavy fermions, intermediate systems, and heavy fermion problems. Okay. The outline of my talk is resumed here. I will give some, show some part of the work in these two systems. I also try to show some new results in the system, and there will be a poster this afternoon that will be presented by the PhD student, which is developing this work for his thesis, and some conclusions. Okay. And as I said, I decided to make a very introductory talk about heavy fermions. There are many students that are just at the beginning, and there are some other students that are not working in this area, I mean, heavy fermion systems. So I decided to give just a small introduction, very simple for these beginners. Okay. So we mainly work with cerium and ytterbium-based intercompounds. Okay. So for normal metals, we have the specific heat dominated by the phonon contribution. Okay, and only at very low temperatures, much smaller than the Bayer temperature, you have the electronic specific heat dominating the specific heat, and this linear contribution, okay, given by gamma T, where gamma is this constant here, okay. But in heavy fermions, the specific heat is typically 100 or 1,000 times that observed in normal metals. And this also, it keeps varying is the temperature. And you see here some examples. This is the most known example of heavy fermion material. And you see gamma, how big it is at going to zero temperature. Okay, and this can be more than 1,000 times the palladium and sodium material. Also, the electrical resistivity of the normal metal is dominated by phonons, and at very low temperatures, actually for some metals below 20 K, you have an independent contribution of the resistivity, independent of temperature, I mean. And that's the residual resistivity that's dominated by defects and imperfections of the leads and impurities. Okay, but in heavy fermion materials like cerium aluminum free, you have a contribution that is proportional to T squared. That is the electron-electron contribution. Okay. And you see here at the low temperature, this is the inset. And I think Professor Coleman has shown this this morning. So I think everybody already knows this problem. So you have here whole proportional to 8 squared that is not observed in normal metals. As I showed, the whole is tending to independent temperature behavior in normal metals. Okay, so this is very interesting problem, and we can summarize this in the case of intermetallic compounds, the kind of system we interacted here. We have a collection of magnetic moments, paramagnetic moments embedded in a fermion C, okay, electron C, and at some, and not correlated, and at some temperature, below some temperature, they become develop some correlation, and you have a very strong renormalization of the free electron mass that can be 100 or 1,000 times the free electron mass. Okay, so the definition of heavy fermion material is mainly this. You have the electronic mass renormalized in such a way that is becoming much bigger at low temperature than for normal metals. Okay, so there is in this case there is a competition between two energy scales. And when you switch this correlation between the electron and the localized moment and the electrons, you have these two energies competing with each other. And for some, here, let me just tell you, because since Professor Coleman already gave you many of these ideas in the morning, so, but I try to control myself and try to explain better. So J is the exchange between the conduction electron and the localized moments, and W here is the bandwidth of the conduction electrons. So this is the control parameter that of these two competing energies. Okay, so for some parameters that is called critical, okay, the NPQI can win this competition, and then the system has a magnetic ground state, or when this parameter is bigger than this critical parameter, the system becomes Kondo compensated, or eventually in a parameter where this is equal to this critical parameter, you can reach what is called a quantum critical point. That is a transition, T equals 0 transition. Okay, So here is a representation of these two competing energies. I think the microphone is not in a good position. So in the picture of Doniak, you can describe this problem by a phase diagram like this. Actually, this phase diagram had some contribution of Professor Musso Continentino, okay, where he suggests the existence of this coherence line, okay, but mainly you have the magnetic line that is controlled by this parameter, this exponent, and this the critical line that's controlled by this parameter, and you have a non-Fermi trajectory where you have some special properties, changes of the properties here in this point critical point. Okay. So this is the typical phase diagram for this kind of systems. Okay. And at this quantum critical point, many surprising, let's say like this, surprising properties can appear, okay, like superconductivity in these materials. And I suggest you to read this paper of Professor Koelman that is very interesting. He gives us very nice picture of all this problem and all these strange properties that is appearing in this quantum critical point. So what we want in this in our work actually is to contribute a little bit to understand what is happening here. That is still object of studies, and it's not well understood. Okay, so we are, as experimentalists, what we do is to synthesize materials and study its properties and try to contribute a little bit more for these studies with more data. Okay? And in our, so I will explain a bit about our laboratories, our experimental setup, and this is actually in our laboratory we have three kinds of pressure cells. Okay, we use pressure as the control parameter to change the properties of these materials. Okay, and now we are starting to apply magnetic field. It was not an easy business for us in the beginning, but now we are already starting this. But this work was made only with pressure. Okay, so our control parameter to build these phase diagrams in the systems is the pressure, hydrostatic pressure. Okay, we have a Bridgman cell that can go up to 15 GPa, and this is a typical installation for this pressure cell. You see here the sample, and you see here the lead. The lead is used as a pressure manometer for this kind of pressure cell. Okay, this is not easy installation. Actually, Professor Eichler did himself this installation here. And this is just an example. It's not the cerium platinum here. Okay, it's just one typical installation I decided to show you, but it's very nice, very beautiful. Yes.
What did you use to stick your leads?
This is silver paint. Actually, is a box. Okay. The glue.
Right. I was just wondering what material you used to make the springs out of.
The springs?
Yeah, it says springs there.
Well, this pressure cell, let me tell you, this came from Germany. Professor Eichler brought this cell. I don't know very much about the construction of this cell, how it was constructed. But these anvils are made of tungsten carbide. This external part is all beryllium copper, okay? This is beryllium copper. And this is internal here is also beryllium copper. Only the anvils here is made of tungsten carbide. It's not very easy to work with. So this is the anvils here. And this around is pyrophyllite, and this in the middle is the soapstone, white soapstone. That is actually the pressure medium for this pressure cell. Okay, so this that gives the hydrostatic pressure cell. And also we have a diamond end cell that was made in Cologne by Professor Elmegid. They built this pressure cell there and they gave it to us. And this is a diamond end cell with, you see here the end, okay? And this is one typical installation, but I guess it's not very good to see. But you see the contacts, you see the sample in the middle, okay? And this goes up to 22 gigapascal. It means the size of the anvils can only support this pressure here, okay? We have a system to calibrate the pressure. You have a ruby inside here, and you see the change of the line of ruby with the pressure. Okay. And also I'd like to show I would like to show our clamp cells. That cells are made here at CePt in our machine shop. Okay, and this is all made of copper beryllium, but the inner part is I cannot show you here, but the inner part is built with ceramic P35N, and these cells can reach 25 kilobars. Okay, sometimes more. It depends how it is when you close everything. If everything's okay, you can reach a bit more. And this is a typical installation for a sample that is maybe 1 millimeter per 3 millimeters long, and it's normal, let's say, silver pen. So we have a dilution system that can go down to 40 milli, but when you put the pressure cell, in general can only start from 100 milli, because the power cooling is not so big for these pressure cells. Okay, you have make AC resistivity in general. This is our AC resistivity system, and you have cryostats like that with magnets inside, superconducting magnets, and you put this stick inside the cryostat like this and apply the magnetic field in some cases. We have a cryogenic laboratory that provides also the liquid helium and liquid nitrogen. And well, I'd like to show you much more, because we have many other laboratories, most ball laboratories and thin film laboratories, but this is not related with this work, so I hope you have time to visit our laboratory sometime. I don't know if it's in the program, but okay. So let me present you the system. The first system we work with is cerium platinum. It is chromium type, chromium boron type orthorhombic material. It is a ferromagnetic system. It's TC 5.8K more or less. But you see this structure, it seems, you see platinum and cerium, they are in the like layer, okay? And this is very easy to see that you have made by layers of platinum and cerium, okay? This is cerium platinum is one of the few examples of ferromagnetic materials that has enhanced gamma value. I didn't put here, but it's heavy fermion, moderated heavy fermion. And there are a few examples in the literature, and one of them is cerium 10-2 that I work in my PhD thesis. Okay, I work with pressure, but doping with iron. And in this work of Sulo, he do high pressure studies in this system, and also he compared with the doping with germanium silicon. And then in both cases, this system seems the ferromagnetic transition seems to give a place after some pressure to another kind of ordering that can be anti-ferromagnetic. That's not very clear, but it changed the ordering. And as in my system, when I dope it with iron, it also there is indication that the ferromagnetic changed to an anti-ferromagnetic with the pressure and with doping.
What are the fixed boundaries? What measurement was done to determine these boundaries? What measurement was done to determine
this is resistivity mainly, but they have susceptibility also here, okay, and also specific heat, if I remember well. Okay, and here they show the behavior with the doping, germanium, see?
Excuse
and,
me. How do you define that line between non-Fermi liquid and Fermi liquid?
What do you mean?
Well, there's a line.
This line. I mean, this is a piece of the work of Sulo, okay, and this is with the pressure, okay, and this system. Here it enters a linear behavior and resistivity in this point. You understand? Okay, this is resistivity. I think they do here this the AB material. There is another system, cerium, silver and antimony. And this system also seems to go to an anti-ferromagnetic phase before it reaches the quantum critical point. So there are one more example, few more examples, but all of them seems to change the kind of ordering before they reach the critical point. Okay. And what we intended to do in this work was to collaborate with one more ferromagnetic system and try to build the phase diagram with this system and see if this system could go to a quantum critical point without changing the magnetic order. Okay. The kind of magnetic order.
How transition from ferromagnet to anti-ferromagnet focus? Is it the second transition or first transition?
Sorry.
In a previous figure,
yes.
You showed there is a transition from anti-ferromagnet
Yes.
to ferromagnet or the other way around. How the transition is done? Is it the first order transition or second order transition?
I don't know. I think it's second order transition. I'm not sure. No, first order transition. Sorry. First order. But I don't have all the data for this material, but they only show this. And also they did some ESI experiments in this system, so they could check the kind of order for that system. And then in our system, at cerium platinum, we don't have any, let's say, measurement to check the kind of magnetic structure in this system. Okay, we're still looking to do this kind of experiment. But this is a work of Victor, where he do the first experiments in this system And as he put the pressure, you see that the transition temperature goes up. Okay, and then we completed this work with the Bridgman cell, and this is some measurements. Okay, we also have lanthanol to take the formal contribution of this material. Okay, here we take the formal contribution, but we don't make the lanthanol platinum under pressure. Okay, we only take this contribution, guessing that this system doesn't change very much with the pressure. Okay, and then here we have the serial platinum with the pressure, and you see how it evolves. The transition temperature is going down, and here there is also some susceptibility measurement that was done by Professor Eichler in Braunschweig, and you see that the transition goes down, but the shape of the curve doesn't change very much. Only the temperature is going down and the signal is decreasing. Okay, we see here in the resistivity at high pressures that a linear behavior. Okay, and also after this pressure, you start to have another kind of behavior, and we plot here in a log scale, and you see a power law for T to square root, okay, and above such a the coherence temperature, okay, we define the coherence temperature, the coherence below which the system has a square behavior in the resistivity. Above this temperature, the system has a power law behavior, and this power law is given by this formula, and where beta is d plus 2 divided by zeta, zeta d is the dimensionality of the system, okay? So we found this exponent for this power law behavior that is related to a ferromagnetic quantum critical point with zeta equal 3 and d equal 2, because it's very close to 4/3 value of beta. Okay. So in the magnetic side, we analyze this material with using the spin wave scenario for an isotropic antiferromagnet, where the dispersion relation for the magnons are given by this. Okay, we also subtract the lanthanol contribution of the formal contribution of this system. Okay, and in this scenario of spin waves, you have the resistivity given by this kind of formula. Okay, and here we show for two examples of for low pressure and high pressure how these two terms of the resistivity behaves. Okay, you have this what we call a spin wave contribution, and this what is called electron-electron contribution. Okay, that's given by this formula here, and you see how it is. The spin wave contribution is dominating the behavior, and also for high pressure we still can get a very good fitting of this behavior. This is just to point out that this is for in the case of an inotropic ferromagnet, okay? Because there is another scenario for anti-ferromagnetic spin wave that you have a bit different formula for the resistivity, And in general, when you try to fit with the other kind of formula, you cannot describe this behavior here. Okay, so it's a hint for us that the spin wave scenario for an isotropic ferromagnet is working from low pressure up to high values of the pressure. It means that the system is keeping its ferromagnetic character even at high pressures. Okay.
What is that third? Additional M2 times CePt.
Yes, this is the electron-electron contribution, but then you don't have a 2 here, but you have an exponent that can vary in this. Okay, it can be not integer either. Okay. So within this scenario, we could, of course, have the how Tc varies, is the pressure, and also the gap of the magnons here. This is the gap in the spectrum of the magnons. D is the stiffness for this spin wave materials, and you see that the gap follows a power law that could be well fitted with this power law. Sorry, with this this law. Yes, this law. This actually linear. Okay, with the difference between the Pc and the pressure, okay, and this could give us a critical pressure that is around this 12 gigapascal, and it's in agreement with this behavior. You see, from linear behavior to some square behavior after this pressure here. Okay, and within this is a spin wave scenario for a two-dimensional ferromagnetic spin wave. We can get this kind of relation between the transition temperature and the gap of the magnons. Okay, and this could fit our. It's not well shown here, but this could fit well this Tc, the transition temperature in this near this point, this critical point. Okay, this could describe very well this line, this critical line here, and this is a hint that there must be some reduction of dimensionality in this system, in this critical point. Okay. So above the quantum critical point, we could follow the coherence line, fitting our resistivity curves, and this is the coherence line. And also we could get the electron-electron coefficient, and you see how it diverges near the quantum critical point. Okay, and this is the obtained exponent is 0.6. That is, and also the coherence line follows the mean field theory for this exponent is 1.5. Okay. And after I resume, just want to show you all the data and continue with this. We go to Ethereum. Ethereum has a kind of a mirror behavior for in this of these serial systems, and in this case, this is a new material. And it has another kind of structure, the tetragonal structure. okay, and also is moderated heavy fermion. But you see that you also have some layer of ytterbium. You see some kind of layered material, okay? This system, as I told you before, is a mirror system. So it starts from the non-magnetic behavior, and as of high pressure, it goes to magnetic side of the diagram. Okay. You see here very well how Tn is evolving with the pressure. Okay. And for this material, here you have for zero pressure, the linear behavior in a very large scale here. And as you apply pressure, this linear behavior is decreasing. See, it's going to low temperatures. And above some coherence temperature here, you see also some power law, and the resistivity is can be described by this kind of power law, and with this exponent between 1 and 1.5 in the case of non-Fermi liquid behavior. Okay, and within this behavior here, epsilon given by d over zeta, and the antiferromagnetic system zeta equal to is describing a quantum critical point with in a two-dimensional spin fluctuation.
The x-axis here is p square plus not p.
Here?
Yeah, x-axis is t square, not p.
Yeah, no.
T squared. Yeah. Is it
Why?
claimed that it's T squared?
T square, right?
Yes. Here it's t square.
Yeah, but then the x-axis is t square.
Okay, so when you make the diagram, we see that the coherence line is dominated by a linear behavior. Okay, and if you try to get the exponent of this coherence line, we see that is the linear term. If you relate it to this kind of scaling. The linear behavior is dominated by this linear term. That means that zeta must be equal to, that is the case of an antiferromagnet near 2D spin fluctuation model near the quantum critical point. Okay, and this is the antiferromagnetic line, and this is our phase diagram for this system. Also, we have the coefficient, the electron coefficient for this system, and you see how it diverges near the PC. Also here we have the residual resistivity, and you see a big drop near this quantum critical point, the residual resistivity, that may be because of the ordering of the moments in this region, and then you decrease the scattering of the quasi-particles, and then you see this big drop here. Okay? So again, using the spin wave scenario, we can try to fit this resistivity in the magnetic side, and for an isotropic antiferromagnet, the dispersion relation is given by this. Okay, and the resistivity given by the spin wave is given by this formula. Okay, and then we fit our resistivity data, and we can obtain the gap of this magnetic spectrum. And also the Tn is given by this, in the case of a 2-dimensional antiferromagnet, the Tn is given by this relation. Here it's nice to show you that in a 3D system, Tn is given by this formula. And you see, as delta tends to 0, Tn tends to a constant value. But if you go to a 2D system, when delta tends to 0, Tn tends to 0 as well. So, since you have a system where the delta and Tn, okay, they have the same trend. As Tn goes to 0, delta also goes to 0. And then this is a hint that this system, in an antiferromagnetic case, in an isotopic antiferromagnet, this may be a behavior like this, that delta Tn goes to 0 as delta goes to 0. Okay?
Question. I mean, apart from these fits, do you have any reason to believe that it should be 2D? What structural aspect?
Another thing is, as you do this fitting, the stiffness, it becomes, it stays constant. Okay?
Is there any reason of frustration or?
Yes, because since the stiffness stays constant, okay, you think that only the softening of the spin wave mode is not enough to explain the gap going to 0. So it may be the system has to become 2D to have this gap going to 0. So this anisotropic gap has to close as Tn goes to 0. Okay? So this is, since the softening of the spin waves cannot explain, since it stays constant, because this is a free parameter in the fitting, okay? So you have it constant.
But it's a blatantly three-dimensional metal.
Yes, but as I showed you, yes, probably, because as I showed you, it has layered. It's a layered material. So it may be, as this Tn goes to 0, you may have some frustration and makes this system to behave as a 2D-dimensional, and then in the anisotropy, it's vanished. Okay.
When you apply the pressure to this layered system, is it equal in all directions?
It's a hydrostatic pressure.
It's all good.
Yes. And in this system, in general, you have a decrease. I mean, in the system I worked in my thesis, I did it was easier because I did the substitution, and it was very easy to see that substitution with iron and pressure gives more or less the same kind of effect in the system. And in general, you have a decrease of the C parameter and the A parameter, but a bigger decrease in the C parameter for this tetragonal system. So the volume decreases 10% more or less in some cases. So the hydrostatic pressure, the main effect is probably the C parameter decreases more. Yes. So here, and also in the case of 2D, two-dimensional, the Tn is described by this formula, okay, and this could fit very well our Tn line, okay. So this is one more hint that this could be three-dimensional system, okay, near the critical point, of course. And here, as I told you, Mariella will show the poster after this. We are studying this kind of material, okay? And this has for this doping. It has a New temperature 4K. It's also a moderated heavy fermion, and here is the transition temperature And as you apply pressure, again, you go to a linear behavior here, low temperatures. Okay? Push. Here we could very nicely build the phase diagram for this system. You see TNL and T coherence, and also the T maximum, the maximum that we related to on the temperature, and this is the phase diagram. But the T coherence, okay, and the A parameter that we took from this square behavior here, it's not diverging with so faster as in the other two systems I showed you. So it may be because of disorder in this system is very high, since this kind of doping in general introduces a lot of disorder in the system. Okay?
I have a question. How does that T max on your previous slide relates to the quantum temperature?
This is a system, as I showed you here. We look at this T maximum here. Okay? If you take the phonon contribution, you see that there is a maximum, maybe related to the quantum temperature, the coherent scattering of this.
Would that mean then that it goes down as you sorry, it goes up as you increase the pressure?
Yes. Yes. If you do the complete measurement, you can follow this very well, because this really something very reproducible. And here, these two systems we presented, it seems that it's showing that these magnetic interactions has to go, when you go near the quantum critical point, it seems to have a bidimensional character, and that is probably controlling the physical properties of this quantum critical point of the system. And maybe is the main scenario, or let's say that we can say that maybe become a universal scenario for this kind of for explaining the quantum critical point in this kind of material. I don't know. This is our contribution to this kind of.
What is EP constant difference?
Sorry? Where?
Left hand side.
Here,
Delta.
this is stiffness. And this delta is the gap of the electromagnet. Okay? This is another way to plot this integral. We just put on the way around to have more or less to compare both phase diagrams. Okay? So that's all I have to say. If you have any questions?
Question time.
So I'm curious, the shape of the phase diagram in the cerium platinum seems to sort of change at around 11 kilobar. Like, sort of, there seems almost to be a discontinuity in the slope there.
You mean here?
Yeah.
Oh, I don't see. I mean, it seems to be very continuous decreasing of the PA. I don't see. Maybe you have some scattering of the points, but this is just normal. That doesn't look like a discontinuity really. You have a lot of points here, and you have a very, very continuous behavior. It's just some scattering. Let's say. It's sharp drop, but not very much. Here, unfortunately, we don't have many points here, so it's really something we have to work more with this problem.
Question?
Everyone wants to go to the poster session.
No.
Yeah.
The people are worried about but everybody now has to talk here. Come to my place.
Okay, so
Okay, so now we're going to have a short presentation. So no mistake.